Okay, welcome to Lesson 11. So we're going to talk about introducing comparative studies because the point of a lot of statistics is to compare two or more groups to one another. So we're going to introduce the idea of observational studies and experiments. So some vocab. Experimental units, they're the smallest collection of individuals to which treatments are applied. So think, are you applying the treatment to a group or to individuals? That kind of idea. So, and examples are often going to be humans. We tend to call humans subjects. They tend to not like to be called units. It tends to offend people. Just a hint. Plants, plots of land, animals, etc. And then observational units. They're the individuals on which data are collected and recorded. So most of the time, at least as far as we're concerned, we are going to have our experimental units and observational units be the same. But know that it is possible that they aren't. For example, I might have a traditional and a hybrid type of course that I teach for ST201. And if I apply it at the class level, my experimental units are the classes, and the observational units, if I collect the exam scores, will be the individual students in the class. So just a caution. So typically, it's going to be very frequent that they are the same. So Araceli wanted to find the effect of watering a new species of cactus. So they go ahead, they take 20 plants, and they have them all in their separate pots. They assign half to not be watered and half to be watered. 1 gallon a day for a year. That's a lot of water. So then they record the change in height for each of these plants. So the experimental unit. So what's the treatment here? It looks like it's water. So to water or to not water, where are they applying it? So each individual cactus. And this is where it's important that we kept them all in the same pot, in their own pots. Observational units. So they looked at the change in height, and they looked at the change in height of each individual cactus. So most of the time, oops, we combine letters here. Most of the time, we will go ahead and look at scenarios where the experimental units and observational units are the same, but know that it's possible they aren't. And usually it is another step beyond what we're doing here in ST201 to address that issue when it happens. So now, I hinted that, yes, there's the scenario where they are the same. Here's one where they could be different. So Eureka wants to test the new superfish food, which is hopefully obviously a made-up name, to the old brand they've been using for their goldfish. They give one tank that has 20 fish in it, the new food, and they have another tank with 20 fish in it, the old food. So, I don't know, you have fish in it, right? So tank 1. And I'm sorry, I'm not going to draw 20 fish. But, tank 2. So now they go ahead, they record the change in weight in grams after 1 month. So the experimental unit, so they have the food. The food is the treatment, the food is what's different between the two groups. So where do they apply it? They don't apply it to the individual fish, right? It would be really, really difficult to feed individual fish. You put the food in the tank. So the 2 tanks. So each tank is an experimental unit. The observational unit, so what did we record? We recorded change in weight in grams. What did we record this for? Each individual fish. And there were 40 of them. So here's an example where experimental units and observational units are not the same. And there are some extra steps because here you really can't assume, like fish in tank 1, they have to share all the same food resources. So if one fish got more food, that means other fish got less food. And so you have to kind of account for the fact that they're in a related tank. Okay, so some more vocab. Factor. So the explanatory variables in an experiment, factors can have levels. So this is like what I was getting at. I'm like, hey, what makes the groups different? Oh, it's the fish food. That was my factor. And the levels would be the new fish food brand and the old fish food brand. So treatments. So it's the specific condition. So if you are doing an experiment and you apply a condition to the individuals, they can correspond to the levels of the factor. So with the fish food example 1, my treatment, I had the new fish food brand and the old fish food brand. Those correspond with the factor, which is food. My control group. So this is a treatment group that receives inactive treatment or an existing baseline. So suppose I wanted to look at a new cancer treatment. We are not going to compare it to nothing because 1, that's super unethical. What we want to compare it to is the standard procedure. Like whatever treatment is standard right now, let's compare the new treatment to that. See if it does better than that treatment. So it's some sort of default baseline that you want to compare to. And then response. So this is what you actually measure. What is the outcome that you're measuring on the individuals? So introduction to comparative studies here. It's designed to compare the differences between 2 or more groups. So you can compare just 2, but as you get more advanced, you can compare more than 2 groups. So for example, we have a manufacturer that makes rubber seals, and they want to compare the average strength of the seals made from 4 different machines. So they have machine 1, machine 2, machine 3, machine 4. And they want to compare the strength of the seals each machine makes. So to test this out, they go ahead and they measure the tensile strength from 5 randomly sampled seals. So here, my factor, what makes the seals different from one another? It's going to be machine. And the levels are machine 1, machine 2, machine 3, machine 4. My treatment is going to come down to the same thing here. It's going to be my machine, and they'll correspond to these levels here. Experimental units. So here, I'm going to go with observational units. This is a little funky. So observational units, it's going to be the individual seals. They recorded the tensile strength for each individual seal. And there were 20 of them. And the response is what did I record on each of these 20 seals? And that is tensile strength. I'm not familiar enough with tensile strength to tell you the units, but perhaps you have somebody like in engineering or something like that that could give you a little info on that. So observational studies. So it is named for what we do. We largely observe. We don't impose any sort of treatment. So we observe and collect info on our units, but we're not attempting to make 2 or more different groups. We're not applying a treatment. It's based on whatever the individuals choose to do themselves or are doing. So when to use, specifically when you want to compare groups from in a sample, you might be looking at survey or demographic data. In part, you have no ability to assign things like, oh, I want to know how the different genders view the vice presidential debate. Well, you can't assign people, well, you shouldn't assign people's genders, right? So you have to observe, like those genders are defined outside of the researcher. The researcher doesn't define them. This is also when you use retrospective data, because you have no ability to assign treatments after the fact, after things have already happened. So it's really important to note that if you have an observational study, you cannot say that one variable causes changes in the other variable. And this is because you could have a working variable that is not accounted for. So you might have a variable that's associated with whatever the factor is and the response variable. It makes it really difficult to isolate, like, yes, this is the cause of the difference we saw. Very difficult. And we'll throw some examples out too. So like, for example, does cheese cause degrees? So we have a really high correlation. It's a correlation coefficient of 0.96. That's a really strong relationship between mozzarella consumption per capita and civil engineering degree doctorates awarded. You do not want to conclude that, hey, let's all eat more cheese so there'll be more civil engineering doctorates awarded. That's not how this will work. So yes, these are strongly related, but there are probably other factors involved besides just cheese consumption and doctorates awarded. So then I want to talk a little bit about, there are two main types of observational studies. There's a prospective study. So a prospective study records the explanatory variable first and then follows the subjects and records the response variable. So this could be like immediately after, this could be years later. It really totally depends on the design of the study. So for example, if you're interested in the link to smoking and lung cancer, you might locate 1,000 participants and ask them whether or not they smoke. Then 15 years later, follow up with them and inquiring whether or not they developed cancer. So we first ask them whether or not they smoke. And then the response is whether or not they develop cancer is what we're interested in finding out. We recorded that later. Versus a retrospective, and I hope this, so pro means like forward, retro, like, oh, that's retro, oh, that's old school. A retrospective study finds subjects with response values of interest and then asks them about the explanatory variable after the fact. So for example, if I'm still interested in the link to smoking and lung cancer, suppose I find 1,000 patients that have developed lung cancer, and then I ask them if they smoked in the past. So we're recording the two variables in different orders here. And it comes down to sometimes there are events and you really can only record, retrospective studies. Like you have to go ahead and say, oh, well, maybe these two things are related, and you have to do it after the fact. They both have their own uses. They're very, very useful. Just make sure you're not making cause and effect relationship conclusions in your results. So confounding variables. So want to bring in, so working variable, so it's not among the explanatory or response variables, means you didn't record it. Right? It's lurking. It's somewhere. Maybe you might even be aware of what it is, but you didn't record it. And it can influence the response variable. So working variables are really bad because you have no information there. A confounding variable occurs when two or more, it could be more, variables are associated with each other in such a way that their effects on the response variable cannot be distinguished from one another. So you have two variables that are related in such a way that you can't isolate, oh, this is, the effect of this variable and this is the effect of that. They're so entangled with one another, you can't isolate their individual effects. And this is not ideal, and we have, in experiments, we have ways to try and reduce confounding. But with working variables, there's really little to do about it. If it's something you didn't record, we can't fix it. So, well-designed experiments, they're going to take steps to avoid confounding. So, a couple of examples here. So, we have in the NBA Finals, the Dallas Mavericks defeated the Miami Heat. So, we're talking basketball. One headline read, Miami's real problem this series, not enough high fives, citing an observational study that found teams that have more touching and high fives early in the season had better performance. The article goes on and it implies if you give more high fives, you score more. You have better basketball performance. So, I invite you to think a second. Is there something wrong with this logic? So what's wrong with using the language, giving high fives improves basketball performance? I would argue this language implies that if you give high fives, it causes. That's the problem. We don't think giving high fives causes people to get better at basketball. Unless, you know something about high fives that I don't, but usually that doesn't cause basketball to be skills to be improved. So then it invites us here, name a few confounding variables that could be explaining why the team who gave more high fives are associated with better performance. So what are some reasons that teams with higher high fives and better basketball performance, like some reasons that might be? So, for example, this is just one, how well the team gets along in general. So if the team gets along really well, they might be more comfortable giving high fives. They might perform better because they are really comfortable with one another. How long people have played together could definitely impact that, because a lot more people are more likely to be more willing to high five folks that they know well versus people who are practical strangers. So, and that would also help improve people's playing. So there are a number of factors that could lead to this. Observational studies. I kind of hinted at this one back when we said, hey, correlation does not equal causation. But a refresher, so this is similar. A recent study indicated ice cream sales and number of accidental deaths from drowning have a strong positive correlation. So what are some possible reasons for this strong association? So, just making through. Buying and eating ice cream causes accidental drowning. It could be true, but it probably doesn't. I like this one. People eating ice cream in the water, they get distracted because ice cream, and they forget to swim. Hence, they drown. And then here's the last one. Warm weather could be a lurking variable. People are more likely to buy ice cream and or go swimming during warm weather. So, I would argue this here, that I wouldn't say that ice cream is causing the drowning so much as ice cream sales are related to the weather, and people swimming are related to the weather. Okay, so that's for it for lesson 11. We'll see you for lesson 12.